Good morning, Dr. Chan. This is Group 3. For this project, we'll be talking about an adjustable hinge elbow brace, a common medical device that many people use for support after an injury or surgery. Our goal is to show how we can apply the concepts we have learned in statics and mechanics to understand the forces and stresses acting on this brace and to make sure it's designed in a way that keeps users safe and comfortable. Throughout this presentation, we'll cover the following topics, which are the introduction, objective, methodology and calculation, discussion, limitations and improvement, and finally we'll discuss our conclusion.
Hi, I'll be explaining about our medical device, which is an adjustable hinge elbow brace. So it is something that is very useful in many situations. For example, after surgery, when your elbow needs support to heal properly, this brace will step in to provide that stability and make sure that the recovery process goes smoothly. It is also a lifesaver if you're dealing with injuries like sprains, fractures, or ligament issues. It helps your elbow to be protected while still allowing some controlled movement so you can heal without making your injury worse. It's really about giving the right balance between stability and mobility. Objective of our assignments. First of all, we would use free body diagrams to perform equilibrium-based analysis for various structures. Second of all, we would solve problems involving a body under the action of axial, bending, or torsional load. And then we will employ moment and inertia-based analysis for problem solving due to compound load. Fourth, we will evaluate stress and deformation of our biomedical devices. Fifth, we will perform effectively as a team in analyzing the real-life example of static objects under loading.
We have covered the background and overall purpose of our analysis. Let's dive into the methodology and calculation we use to evaluate the adjustable hinge elbow brace. We broke the analysis down into 5 main areas. First, torque and moments. We'll start by examining the forces acting on the brace and how they affect its balance. Torque. Then, we calculate the torque on the arm when wearing the brace and how it impacts the design. Torsion. We will look at the torsion acting on the steel plate at the hinge and how it affects the stability of the system. 4. Shear stresses. Then, we calculate the shear stresses on the arm and ensure they are within a safe range. Fifth, strain on nylon ribbons. Finally, we analyze the strain on the nylon ribbon to make sure it holds up under the load without excessive stretching. By examining this area, we can identify any potential risks or weaknesses in this design and ensure that the brace provides the necessary support while preventing injury or discomfort. Let's start by looking at the forces and moment acting on the adjustable hinge elbow brace. The first step is to create a free body diagram of the elbow brace to help us visualize all the forces acting on the brace. To set the scene, we have the following values to ease our calculations, which are mass of student M1 equals to 45 kg, mass of arm M2 equals to 2.5 kg, gravitational acceleration G equals to 9.81 meter per second square, length of posterior arm L1 equals to 0.35 meter, length of forearm L2 equals to 0.23 meter, length of trunk L3 equals to 0.31 meter, and the coefficient of friction mu equals to 0.4. Then we calculate the friction force, which is F1 and F2, by using the formula frictional force equals to mu times N, where N is the normal force acting on the hinge. Then we use the equilibrium equation, which is total Fx is equal to 0, total Fy is equal to 0, and total moment equals to 0 to calculate the force distribution. Next, let's proceed to calculate the torque experienced by the arm when wearing a hinge elbow brace. A torque is a rotational force that tries to rotate the arm around the elbow joint. To calculate torque, we use the formula T equals to F times D times sin theta, where T is the torque, force is the arm weight, which in our case is 24.525 Newton, and distance D is the distance from elbow joint to the wrist, and in our case D equals to 0.115 meter. We will calculate the torque at 3 different angles, which are 0 degree, 90 degree, and 120 degree, to analyze the torque at different positions of the arm. At 0 degree, no torque because the arm is fully extended. The torque is equals to 0.0 Newton meter. At 90 degree, the torque is equals to 2.82 Newton meter, and the torque is maximum at 90 degree angle. At 120 degree, the torque is equals to 2.42 Newton meter, which is slightly less than at 90 degree. As we can see, the torque increases as the elbow bends from 0 to 90 degree and then decrease slightly at 120 degree. This helps us understand how the arm moves and how force affect the brace.
Alright, so moving on, we will have to calculate the torsion on the steel plate used in the adjustable hinge elbow brace. So first of all, we need to assess the torsion on the steel plate at the hinge. So we assume that the steel plate are made of two rectangles and one circle with a radius of 0.02, which moving on we'll be showing the pictures. So for a circular section, the formula would be pi r to the power of 4 over 2. However, for rectangular section, it will be bh to the power of 3 over 12. So then lastly, we will add the result together to get the outcome. Moving on, we'll be calculating the angular deformation of our steel plates cross sections. So as you can see from the pictures on the right side, it shows that the steel plate are made of two rectangular sections and one circular section, as we have mentioned. So now we're calculating the angular deformation for it. So the formula is shown. T represents the torque, which we have calculated. L is the length of the steel plate. J is the polar moment of inertia. And then G is the shear modulus, which is a constant. So we can get the result, which is 6.84 times 10 to the negative 7 radians. So for shear stress on our arm, first of all, we need to calculate the total area of our upper arm and forearm using the formula total area equals to pi diameter over 4. So we have to calculate the diameter first. As you can see from the picture, we are actually measuring the diameter of our arm. So we can get the result of our total cross-sectional area of the arm, which is 0.00385 meters square. Next, we can proceed with the calculation of total shear stresses applied on our arm using the formula of force over area. So first of all, we need to get the force first. Force equals to the weight of the adjustable brace times to the gravitational acceleration. We can get the value of 2.943 Newton. Moving on, we use force over area. We can get the result, which is 764.42 Pascal for our shear stresses. Alright, so moving on, we'll be calculating the stress and strain experienced by a nylon ribbon. First of all, we're calculating the stress. So in this case, force equals to 2.8 kg times the gravitational acceleration, which is 9.81 equals to 24.525 Newton. So moving on, we need to calculate the cross-sectional area. So because the length of the nylon ribbon we have measured is equal to the distance of our trunk, which is 0.31 meter, and then the thickness would varies. So in this case, we're taking 0.05 meter. So the cross-sectional area would be the length times the thickness, which is we get 1.55 times 10 to the negative 3 meters square. And the stress is equal to force over cross-sectional area. So the value we are getting is 15822.85 Pascal. So we can proceed with the calculation of strain. Strain equals to Young modulus over our stress. So as we have calculated the value of stress, and then we have known that Young modulus of the nylon is equals to 3 gigapascal. So we can get the value of a strain, which is 1.58 times 10 to the power of negative 4.
Next, I will continue with the discussion. Force is a push or pull interaction applied on an object to change its state of motion. Force is a vector unit, which means that it has both magnitude and direction. The formula for force is F equals to ma, where m represents mass and a represents acceleration. The SI unit of force is Newton, and moment of a force is a measure that its tendency to cause rotation about an axis. The formula for moment is m equals to Fd, where F represents force while d represents the perpendicular distance. The SI unit of moment is Newton meter, and positive moments rotate counterclockwise while negative moments rotate clockwise. Torque is the rotational equivalent of linear force causing rotation about an axis. Torque determines the rotational motion of an object. Its formula is tau equals to Fr sin theta, where F is force, R is lever arm, and theta represents the angle between the force and lever arm. Torque is measured in Newton meter and it is related to the twisting motion in structures like shafts and joints. Torsion refers to the twisting of a structural member due to its applied torque about its longitudinal axis. The greater the torque, the greater the torsion experienced. For shear stress, its formula is tau equals to Tr divided by J, where T represents torque, R radius, and J is the polar moment of inertia. For angle of twist, theta equals to TL divided by Jg, where L represents length and G represents the modulus of rigidity. It is critical for analyzing torsional loads in cylindrical structures. Stress is the internal resistance offered by a material towards an external force. It is measured by force per unit area. Stress helps us to determine whether the material can withstand applied forces without breaking. Stress, on the other hand, is a deformation of a material under stress. It is counted by change in length divided by original length. There are 4 types of strain, which are tensile, compressive, shear, and bending stress. For the Young modulus, it is equals to stress divided by strain, and its unit is Pascal PA. High modulus indicates material rigidity.
Hello, my name is Fatima, and I'm going to describe the limitations with the adjustable hinged elbow brace. And as a set example, I'm going to use the Orthoman hinged Jerome elbow brace because while there are a lot of adjustable hinged elbow braces, I feel like this one is the perfect choice since it's already been in the market since 2019. So it's not too old to a point. It's not using the most advanced technology and resources, but it's not too new to a point that people haven't still discovered the faults with it. And since it's been in the market for more than 5 years, that's when people start discovering the faults after a while. So the limitations with this device that people found out are, first of all, the device weight. Since the device weighs for 1.39 pounds and uses aluminum alloy, at first you don't really notice much of the heaviness, but after you go for a walk or you sit at a desk for an extended amount of time, that's when you start feeling sore and you feel like it's getting heavy. Next, we have limited adjustability because while the elbow is obviously adjustable, the rest of it isn't, and the cubital fossa, people complain that this area under the in the elbow band basically that the guy is also pointing at, it starts turning red and it starts showing marks and it also starts getting painful and irritated after a while, and that's not really an adjustable thing within it. So that's another limitation of this device. Otherwise it would have been revolutionary. Next, speaking of skin irritation and redness and marks, skin irritation and discomfort is another like huge problem since the material is made out of laminated foam material. While breathable, it does cause friction and heat and pressure after a while. So it's really dangerous for people with sensitive skin, people who have eczema, psoriasis, and more. So luckily, with the previous limitations, there could be improvements. And the first improvement that could be done is redesign for weight optimization. So we could use lighter materials, like instead of aluminum alloy, we could use carbon fiber composites, which are apparently 42% lighter, while being 8 to 10 times stronger. Next, we could enhance adjustability mechanism. We could add either ergonomic padding or gel-like material in sensitive areas, like the elbow band that we talked about previously. And next, we could also introduce precise adjustment systems such as micro dial adjusters for better customization. Because while it is available in the elbow area, that one is adjustable. The other parts aren't really adjustable. They do have straps, but those just help you take off and put back the device. It doesn't really help with anything else. Next, we have skin-friendly material upgrades. We could do that to improve the device as well. We could replace current laminated foam with hypoallergenic silicone-based padding or medical-grade microfiber. So usually the silicone-based padding is used in the base of the shoes so that it helps with extended wear. And I feel like the same technology that is used in like medical shoes could be used in this one as well, and incorporate moisture wicking fabrics to improve breathability and reduce irritation. This helps people who have psoriasis or sensitive skin and get rashes easily when they sweat. So this is also another improvement that could be done.
In conclusion, this project has provided valuable insights into the applications of statics and mechanics of materials in the analysis of an adjustable hinge elbow brace. By examining the various force and movements acting on the braces as well as the factors like torque, torsion, and shear stresses, we have gained a deeper understanding of how the brace supports the arm and where potential failure point might arise. Through our analysis, it is clear that the design optimization plays a crucial role in ensuring both the functionality and safety of biomechanical devices. Moving forward, improvements such as the use of more advanced materials, a more refined design, and additional testing are essential steps to enhance the brace's performance and reliability. This project has not only broadened our understanding of the mechanics involved in such devices, but also emphasized the importance of prioritizing user comfort and safety. By continuing to refine the design and conduct further testing, we can ensure that the future interactions of elbow brace are both effective and reliable for the user.
These are our references. Thank you for your attention.